Okay, hello everyone. My name is Assaf Kadosh, and then I'm an algorithm developer at Elbit Systems, ISTAR and AIW2024. I'm very excited to be here on the stage today. Our talk today will be on AI for multi-spectral sensors. Let's go through the agenda. First, we talk about first we do the introduction, then we move forward to the problem overview and the motivation. Next, we will discuss our deep learning solution and the methodologies, and finally we will summarize it all. Also, we will cover some key concepts like supervised learning, semantic segmentation, data augmentation, pruning, knowledge distillation, and more. I hope you will find it interesting. Starting with the presentation, we will highlight the detection challenges in operational scenarios. First, we have small and distant targets in observation systems. Even more modern high-resolution systems will still face challenges in detecting objects at kilometers distance because they appear as few pixels or sub-pixel size. Next, we have camouflage targets or foliage. Targets are hidden by vegetation or camouflage fabrics, complicate existing detection capabilities. Also, we have the dummy targets that look like real targets. These targets disguised to mimic the real ones, which also difficult to current system to detect the difference. Lastly, we have terrain characterization. Standard systems struggle to identify and classify features like grounds, water bodies, building types, and more. Let's lead us to the spectral sensing system. Standard imaging systems rely only on spatial feature extraction, which limits the ability to detect small objects in complex scenarios. The spectral signatures offer a whole new dimension that helps us to help extract the necessary information. We'll see a short video that explains it. As you see, the spectral sensing system collects data in a multi-dimensional informational cube that includes spectral details of the photographed scenario, rather than an RGB image, the standard RGB image. Each pixel contains a continuous spectrum, allowing us to identify the material present. However, multi and hyperspectral cubes are affected by the atmospheric conditions. If you want to do a target detection on this data, we must remove these atmospheric effects. So it's not simple how you see in the video. Let's go through three basic concepts that will run with us in the presentation today. First, we have the radiance cube. Represent the camera-acquired spectrum intensity per pixel, showing us the optical energy in arbitrary units. Next, we have the reflectance cube that shows the reflectance spectrum per pixel, indicated the percentage of light reflected at each wavelength, which creating us a unique signature for each material. This is the important part. And finally, we have the spectral cube calibration. This process is taking the radiance cube and convert it to a reflectance cube. So what is the problem? The atmospheric effects. The radiance cube are sensitive to external conditions that alter the acquired spectrum, such as ambient lighting, which varies with the time of the day, environment, and weather. Shooting distance amplifies atmospheric effects, while aerosol and humidity concentration along the atmospheric path also affect the spectrum. As we can see in the left plot shows the radiance from the targets in two different times of the day, one in the morning and one in the afternoon. We can see the change. In the right plot, we can see the radiance from the target in two different ranges, one in 3 kilometers and one in 6 kilometers. Let's discuss the deep learning solution to solve all these problems. First, we will start with the radiance cube with no initial registration. This is here. We need to do alignment or registration. This is an optical flow task. Then we will do semantic segmentation for specific targets. And finally, we will concentrate in the radiance cube with the segmented targets of interest. The main problem that this entire solution needs to converge and run on a low budget and very low memory usage, low powered edge hardware that is not a GPU. We will start with the optical flow task, the database for training, how we create the database for training. So we take the radiance cube without initial registration, and we created, and with the pre-trained GM flow, this is a SOTA transformer for optical flow tasks, we created an optical flow teacher maps that will be served to the ground truth in our training. As you can see, we have 2,270 optical flow maps and cubes that are divided to train, validate, and test. Methodology 1. Let's see what is the solution. The name we give to this entire solution, the entire neural network, is GLNets, Global Local Nets. It's built from two parts. The first stage is a semi-global network, semi-global stage, and the second is a local stage. The motivation for these two parts is, the big motivation is to run on a low power hardware that is not a GPU. And the second motivation, it's first we will reduce the space between the two frames. And then in the second stage with the local network, we will do the movements that needed and will fix the wrong movements from the first stage. So let's go through the pipeline. We have two frames, 832 by 1088. Frame 2 needs to be aligned to frame 1. First, we do a hard resize with a factor of 0.2 and feed it into a semi-global network specifically called draft S, and it will run only one iteration. Note the draft architecture is not a global architecture for the optical flow test, it's a local. But because we're doing the factor, the resize, with the hard resize, we're getting a semi-global network. We also see that in the predictions that the movements is global. We get in the predicted flow, we will upsample it, of course, to the full size, and we're warping frame 2, warping the optical flow on frame 2. This will yield us a new frame, and we also need a new flow map to be our ground truth. This will be the original flow map minus the flow predicted, and we will feed the second stage, the local network, with frame 1 that is unchanged and with the new frame. The local network is a flownet squared S, Y squared. We know flownet S. This is a pruned version by us, up to 30 times faster from the original flownet S. And we will get the predicted flow. We warp it on the frame, and finally we'll get frame 2 aligned. Let's see some visual results. In the left side, we see the prediction, the uses of the prediction from the GM flow. Of course, we use the optical flow to align the image, the frames. In the middle, we can see the input. See this? That is not a registered frames. And in the right side, we can see our results from the GL nets. We can see that it look very close to the ground truth. Now we'll see it in numbers. This slide, this plot is the endpoint error in pixels versus the inference time. In the plot, the results is on 237 cubes from the test set, of course. You can see that the rough large with 12 iterations. It's very known optical flow architecture, and it's lead the boards. Gets an EP of 2.2. Of course, he was trained on the spectral data set, and our solution getting an EP that is 2.8, but with impressive FPS of 572 on the A100 card. If you want to project it to cheapest card, like the RTX 2080, it will probably be 200 FPS, 250. Let's go through the next challenge, the next part of the pipeline, detection and classification from radiance cube. As you can see, we have 1,559 cubes, each with a semantic segmentation map. The challenge, as all you can see, is the low amount of the training data. The impact of this low data amount is that the model not be a robustness model. And how we will solve this problem, we did an extensive data augmentation. What is the foundational issues with limited data? We use MOTRAN, an atmospheric simulator, which will simulate various of atmospheric conditions like altitude, visibility, relative humidity, sun azimuth and sun zenith angles, and aerosol models. Also, MOTRAN have models for all the world. Each longitude and altitude have another model. As you can see, we have over 1 million different atmospheric conditions. To use MOTRAN, we must have a reflectance cube. We can use the radiance cube. So we do an offline spectral calibration, and we obtain the reflectance cubes. And then using MOTRAN, we scale over 1 million simulated cubes from each real reflectance cube. From each one, I'm going out to 1 million cubes. Of course, I'm doing it on the fly. I'm not saving the data. This is the formula application. And this leads that we cover the wide range of atmospheric conditions in order that the model will ability to work in various time and in day and year. Another more data augmentation that we do, and we had master do, is to transplant targets in the cubes that ensures the class balance and spatial variability. We start with cubes that may have no targets, or a few of them, to create a strong model, and we augmented this data. Wait, we extract amorphous stains to simulate targets and adjust and blend these stains to match the background texture. The target spectrum areas was chosen randomly in the scenario. And then we blend these targets with the surrounding to make them appear as a part of the original radiance cube. Why we blend them? Because when the observation system shoots, and the pixel will blend with his surrounding. So we must blend this target here with his surrounding. In the last image, you can see a cube with 10 different targets transplanted. Of course, you don't see that. This is the complex scenarios, but believe me, it looks realistic. What is the architecture that we use? Remember, we have low power hardware. We use the nested unit called Unit++. The structure is encoder-decoder, encoder-decoder blocks connected in skip connections. Why it's called nested unit? You can see 1 unit, 2 unit, 3 unit, and the 4 unit. Okay? You can see it from the beginning. All of the units is connected between. But what is the advantage from this in this architecture? First, it captures the fine details. What's it mean? It's ideal for detection small targets. Second, we have the deep supervision method. Okay, this is the red pass. It's in the training only. That improves the gradient flow, the model convergence, and the accuracy for small targets. The third advantage, we have the inference pruning. That means that we can run inference on each sub-unit we have here. You see, this is a very small unit. This small unit, the third unit, and of course on all the model. This approach of inference pruning, of course, we used it. We train on all the model, but we inference only on what you see highlight. Note that this cut off almost 8 million parameters from the model, which give us a very efficient inference while containing the accuracy. To be honest, the accuracy was pretty better. Okay, a little bit, but was better. Let's turn off the lights. Okay, here you see the predictions, the segmented targets, metrics to evaluate. We can see PD and F1 score. PD, I need to be hurry. PD is over 90% average on all targets with low FAR, false alarm rate, and F1 score is average 80%. We'll see a very short video that shows everything, and we will finish. Stop. Thank you everyone for attending and listening. I hope you find it interesting.